Welcome. Today we're going to be discussing electrical energy and power from our previous class, and we are going to concentrate on how to derive the equations that are related to these concepts of electrical energy and power. And also we're going to do some examples to understand how these principles are applied, or these equations are applied in real life. So stating that we'll now go to the board so that you can follow along as the derivation is being done. I would suggest you get a notepad out or your notebooks and copy as it's being done on your note so that you can actually get a good grasp of what is going on. Okay, let's go to the board. Let us begin with electrical power. From our earlier definition of electrical power, we said that electrical power is the work done in moving a charge from 2 points of of potential difference. Okay, so that being the case, we said the work done, right? So we represent work done as W in moving what? A charge, right? And charge from our previous lessons we know is represented by what? Q, right? And potential difference is represented by V. So work done is electrical power, electrical energy, work done in moving charge Q, 2 points of potential difference V. Okay, now we can call that equation 1. Okay, so next, if you recall, right, you must recall this, I suppose, when we had a lesson in, what was it called, electric current, right? We said Q, which is charge, right? So charge is current times time, right? Charge is the amount of current that passes through a point in relation to time, right? So that being the case, if you recall that, and remember that the reason why we're going through all these processes is not just to have long equations. There are certain situations you might find yourself where you might have one value or the other that you can check, right? And you might have a situation where you can't check other values, but you need to find this electrical energy, right? And so you must have different formulas so that even if you don't have all the details, with the ones you have, you will be able to get the results you want. Okay? So that's why we're going through all these processes. So now, looking at this equation, we have Q is equals to IT as our formula for electric charge, right? So looking at that, we can therefore replace Q in the equation of work done with IT. So let's do that. Okay, so we now have a different equation which indicates that W is work done is equals to ITV. IT representing Q here, which has been replaced from the equation 1. So let's finally just put it all together so that it will be neat. Okay, and we can call this equation 2, right? So let's call it equation 2. Now, on to the next step. You see, you will recall Ohm's law from our previous lessons, right? Which says that V is equals to IR, right? Of course, just to clarify, V is our voltage I is current, T is time, and R is resistance. I'm sure you can check this in your textbooks, and we have done this before, so I think you should be able to recall these bits of information. So now this represents Ohm's law, right? And what does Ohm's law state? You will recall that it states that the voltage or potential difference in a current carrying conductor is directly proportional to the current, right? Now what this means is this: if there's an increase in voltage, there's an increase in current, and vice versa. Now what does potential difference mean? Let's use a term that you might be familiar with, or an illustration that you might be familiar with. If you put a water tank up on an elevation or on a high surface, the water will flow faster from maybe a hole in it, right? Because gravity is going to pull the water down. There will be more force on it than if you put it on a level surface, right? Or let's look at it this way. If water is flowing from a pipe and you block it, right, with a small piece of something inside the pipe, deep within the pipe, the pressure will not be as much as if there's nothing obstructing it. It's the same thing, only that in this case the gravity is replaced by electric potential difference, right? So in this case the electricity flows towards the point of lower potential difference from the point of higher potential difference. Okay, hope that helps a little. Now, looking at this our equation, we have V is equals to IR. Now, what do we do next? So using Ohm's law, we can then put it into the equation and we replace V with IR, right? And we get a different equation. So let's try that out. So we now have this as our new equation. Remember that right now we are trying to replace V in this equation with something different, right? And our new equation will be W, which is work done, is equals to I square, right? Okay, and RT. And what would you call that? That would be our equation 3, right? So that being our equation 3, we can now use that to get other equations, okay? So let's do the last section of this on electrical energy, and then we'll go to the next section. But if we bring Ohm's law into this again, we can then find another equation or another way to solve this question, okay? Remember that V is equals to IR, right? And if we make I the subject of the formula, right, then what would we get? That would then give us I, right, is equals to V over R. I hope that makes sense. V. Looking at that, we can now substitute it into the equation and get new values. This then becomes our new equation. W is equals to V all square over R, right? V over R all square RT. Now let's break it down into smaller chunks. So let's try and simplify things. Now if we remove the bracket, we have V square over R square times R times T, right? So if we cancel one R on both sides, right, we have R square at the bottom and we'll have one R at the top. If we cancel the R's, we now get V square times T over R, which is now our equation 4. And that will be all the formulas you would need to deal with electrical energy for now at this level. Thank you.